Ladies and gentlemen, मेरा नाम आज़ाद है, आज़ाद भाई, PhD student, 2012 batch, and I'm going today to defend my PhD thesis. It's titled Separating Fluidized Bed Combustion, Toward Third Generation of Oxy-fuel Combustion. To get started with outline, here we have first motivation and objectives, second cold CFV unit study, hypothesis of pure oxy-fuel combustion, fourth hard CFV unit study, thermodynamic analysis, conclusion, and we conclude with scopes of future work. First, the problem, statement and motivation. As we know, over the world, the fuel consumption is increasing dramatically, especially for coal, which could touch the same value of liquid by 2030. And we can say almost 1/4 of total greenhouse gases comes from coal. And carbon dioxide of greenhouse gases contribute almost more than 50% of the which come from fossil fuel. In 2006, about 42% of the world energy-related carbon dioxide emissions were attributed to coal use. And here we can see the lion's share comes for energy supply, which is the power plant which is used for supplying energy over the world. And coal is widely used in India, in Australia, in Russia, in China, even in USA. And we can see here the world electricity generation by sectors depends on the type of fuel. Coal could take almost 40%. And here we have blue map scenario for mitigating carbon dioxide. First of all, 19% could be mitigated using CCS, carbon capturing and sequestration, renewable energy 17%, nuclear 6%, power generation efficiency and fuel switching 5%, end use of fuel switching 15%, and lastly 38% for efficiency, end use fuel and electricity efficiency for the 30% and less. And here, for carbon capturing and sequestration, we have three main subcategories. One of them, oxy-fuel combustion, pre-combustion, and post-combustion. For oxy-fuel combustion, we use pure oxygen for firing coal, or it doesn't matter, maybe coal or biomass, the solid fuel. For pre-combustion, we use gasification. For post-combustion, after getting the flue gas, we construct from the flue gas the carbon dioxide for sequestration. So far, we cannot see any circulating fluidized bed commercialized because of the expenses of applying carbon oxy-fuel combustion. And so far, the biggest circulating fluidized bed is being installed in Spain with 30 megawatt. This limitation because of the cost of applying oxy-fuel combustion side by side with the efficiency penalty, which could be between 10 up to 30% comparing with the conventional power plants. This penalty comes from air separation because in the conventional power plants we use air directly for firing. Here we need air separation unit to get oxygen, pure oxygen, side-by-side gas processing system, because after combustion we need to process carbon dioxide, liquefy this carbon, and transportation additional to injection. Here the objectives of this work starts with actually we have segregated in two main packages. One of them for cold study and another one for hot study. For the cold study, it's for studying the hydrodynamic behavior of CFB, circulating fluidized bed. And we have started with fabrication and designing of one CFB. We're supposed to answer several questions: whether this mini CFB is running properly, the rate of circulation of the solid circulation is fine enough to work, and we have used the mixture of CO2, O2 to experiment the difference, to find the difference between air and mixture of oxygen and carbon dioxide. For the second package, we have designed and fabricated hot CFB for oxy-fuel combustion, and we have proposed novel feeding strategy for pure oxy-fuel combustion. So far, there is up to 50 or 60% of oxygen in Chalmers University. They have used oxygen concentration up to 50 to 60% with external heat exchanger side by side with augmented rate of solid circulation. So in this work, we have proposed novel method for pure oxy-fuel combustion. And we have experimented, and the objective even not only for pure oxy-fuel combustion. Whenever we are using pure oxy-fuel combustion, that does mean we are not in need anymore for EGR, exhaust gas recirculation. For installing and fabrication and running the power plant, it would be much more cheaper. And we have put one aim for using biomass with oxy-fuel combustion. Finally, conducting thermodynamic analysis for exergy and energy, both of them. Here we may start with cold circulating fluidized bed unit. First of all, why to use circulating fluidized bed power plant, even in the laboratory scales? Usually in the hot bed for firing, the temperature is very high. It could touch 900 degrees centigrade. So for studying the hydrodynamic, for pressure drop, for suspension density, for rate of recirculation, it will be difficult whenever the real power plant is working. So we use the cold one for studying the hydrodynamic, whatever I have mentioned, pressure drop, suspension density, side by side with recirculation rate. And for oxy-fuel combustion in circulating fluidized bed combustor, we aim to compare between air and oxy-fuel cases. Maybe if somebody is not familiar with this kind of power plant, for CFB, we have the main reactor, which we call geyser. Usually there is inventory, which is sand, and here, with blowing the oxidant could be air or mixture of CO2, O2. Side by side, we may feed the coal or the fuel from side or from the return leg. Reaction or fire takes place in this reactor, in this column, riser. And after that, there is cyclone, which is here, capture the solids, the inventory sand, side by side, and burn coal or solid fuel to return back to the riser. That's why we call circulating fluidized bed. Meanwhile, the exhaust go out from the funnel, from this exit. Here we have studied first of all the effect of primary flow rate. Here we have the bed voidage with dimensionless height of the riser. We can see we have used three velocities, 2.7, 3.4, and 4 meters per second, with different parameters. We can say with we found with higher terminal velocity, the bed voidage increased because the entraining of the particles of the solid of the sand or fuel becoming higher. That's why the voidage is higher. Meanwhile, for the suspension density decreases with increasing of the terminal velocity. The effects of operating pressure. We have run this setup under pressuring condition from 150 kilopascal up to 250 kilopascal. We have seen also with decreased pressure, we have higher bed voidage. Meanwhile, for the suspension density, it's increasing with increasing pressure. The effect of aeration. Actually, for this small CFP, mini CFP, we have found for 3 aeration 0.65, 1.9, 3.23 meter per second with increasing aeration velocity. The bed voidage is increasing. Meanwhile, for the suspension density, it's increasing also with the increasing of aeration. The effect of particle size, we can see from 160 micrometer increased up to 427 micrometer. The bed voidage is decreasing. That does mean the amount of solid inventory side by side with the cold particles are higher in the riser. We may note here the drag coefficient alongside with the dP, the particle diameter. Whenever the particle diameter is increasing, the drag coefficient decreases. And we can compare between two particles, a small one and bigger one. Whenever the particle is small, the drag coefficient is much more higher. Meanwhile, the gravity force less. If we replace with bigger particle, in this case, the drag coefficient and the force, the drag force, it will be less. Meanwhile, the gravity force will be higher. That's why in the bed, whenever the particle size increase, the inventory inside the riser will be much more higher. The effect of bed inventory, we have compared between two bed inventories, one of them 500 grams and another one 750 grams. With increased bed inventory, the bed voidage decreased, meanwhile the suspension density increased. Here, for comparing between air case and the mixture of oxygen and carbon dioxide, actually we have found slight difference. We can say almost it's identical between the air case and here between CO2 and O2, and we have compared here between pure oxygen, 35%, 65% oxygen and carbon dioxide, 25%, 75% of oxygen, CO2. That does mean there won't be, you can say, a big gap between the air case, the conventional one, and the oxy-fuel case. We have calculated here the terminal velocity for different particle size for sand with different species for carbon dioxide in oxygen and air and nitrogen at 25 degrees centigrade and 850 degrees centigrade, just to know what's the effect of replacing air with CO2, O2. We have found slight difference between air case and between the CO2, O2. We can see in this picture how this density changes whenever we are heating up. Suppose we have cold bed and hot bed. Whenever we are heating, the density drops. Meanwhile, for the dynamic viscosity, whenever we are heating from 25 degrees centigrade up to 850 degrees centigrade, the dynamic viscosity increases. In this case, we have at higher temperature, lower density, meanwhile the viscosity increasing. One of them compensates whenever the density drops. That does mean the terminal velocity will change, but one of them will compensate the effect of other. And we may conclude with this one. There won't be, for this, at least for this mini circulating fluidized bed, there won't be a huge change. Actually, even for those sensors, they couldn't detect the real difference between CO2 O2 mixture and air. The summary of cold unit study: the bed voidage of this mini CFV is high, more than 80%, 89%. The rate of recirculation rate is moderate, around 20 kg per cubic square meter second. And this one is very important because for oxy-fuel combustion we need more recirculation rate for solid to absorb the heat. This one could be, we may mention later on how it could be enhanced. Higher aeration increases the bed voidage in this mini CFV. Interestingly, the effect of oxy-fuel condition are insignificant compared with the air case. The hypothesis which we proposed for pure oxy-fuel combustion, we may start earlier. There was they used oxy-fuel combustion, but they didn't at the very beginning use oxy-fuel combustion for CCS, for carbon capturing and sequestration. It was used for enhancing the oil recovery. They burned fuel, and the exhaust itself they used to inject it in the oil reservoirs for enhancing recovering oil. And we have enhanced oxy-fuel combustion, another technique which they have used for increasing the adiabatic temperature, for increasing the efficiency. And we can say oxy-fuel combustion with CCS could be a companion between the oxy-fuel combustion for enhancing oil recovery, because the outcome of oxy-fuel combustion could be used for enhancing oil recovery. On the other hand, it could be used for enhancing the efficiency. Here, for how oxygen and lambda, the oxidant stoichiometric ratio, affect the flame temperature. Actually, for combustion, we have three main techniques for, you can say, controlling the fire. One of them, the oxidant itself. What's the percentage of the oxidant? In this case, whenever the oxidant percentage, the oxygen in the oxidant less, the adiabatic flame temperature will be less. On the other hand, whenever the fire and the combustion reaction is running, if we are absorbing heat, that does mean the adiabatic flame temperature will be less. That's what they have used in Chalmers University. In this reactor, they used to recirculate more and more sand side by side using external heat exchanger. In this case, they are observing the rate of heat release. Whenever they are observing rate of heat release, that does mean the adiabatic flame temperature much more less. But on the other hand, lambda, which we have proposed, we can use for can be used for controlling the ideal flame temperature. We can see here for different oxygen concentration in the oxidant from 21% up to 100% with stoichiometric ratio from 1 up to 5. And by the way, the stoichiometric ratio is what's the amount of oxygen required for firing or reacting specific amount of fuel. So stoichiometric ratio 1 represents the required amount of oxygen for fuel combustion in perfect case. When we are giving 2 lambda equal 2, that does mean we are giving twice more oxygen. That does mean 50% will react with fuel, and 1 will be as excess oxygen. And here, for different stoichiometric ratio and different oxygen concentration, we can see how does it vary the temperature, ideal flame temperature. And we can see first one in the oxidant, whenever the oxidant contains 21% only of oxygen, the temperature equivalent to the temperature in case of pure oxygen with lambda equal to 5. Why it's like that? Because whenever we are using lambda equal to 5, that does mean we have 5, 1, 2, 3, 4, 5 volume of oxygen, only one taking place for combustion, for instance, C plus O2 giving CO2. Meanwhile, the rest we are giving 80% are only absorbing the heat. It doesn't involve in the reaction itself. It's equivalent to the air case. It's 79% nitrogen plus 21 oxygen. Only 21% of the oxygen is reacting with the fuel, coal or whatever, and the rest of nitrogen as inert gas, it's not involving in the reaction itself. It's only absorbing the heat. Here, whenever we are giving more oxygen, it's not involving in the reaction itself, but it's absorbing the heat. In this case, if we have used series of reactors, we may give pure oxygen for the first stage, and we may feed fuel for lambda equal to 3. In this case, 1/3 only will react, and 2/3 will be excess oxygen. The second stage, lambda will be 2. Half of this oxygen will react, and the rest will be proposed for the third stage. In this case, the product of the second stage could be used as oxidant. So here, the outlet of the first stage, oxygen, CO2, it's the oxidant for the second stage, and for the second stage, the outlet or the exhaust of the second stage is being used as an oxidant. And here, the same for those reactors 1 to 3, we may use a series of mini CFVs. We may use 2 or 3. In the same manner, we may use primary inlet as pure oxygen. We may feed a fraction of fuel. The outlet of the exhaust of the first stage could be the oxidant for the second stage. Finally, a summary of the proposed hypothesis that in terms of theory, it's possible to control the temperature by stoichiometric ratio, even for pure oxy-fuel combustion, for CFB. Controlling temperature by using stoichiometric ratio could be used with enhanced heat transfer to minimize stages. Because as we have seen here, 3 stages. If we would like to minimize even those stages, we may use only 2. We can use more higher augmented recirculation rate, And finally, this hypothesis needs an experimental validation. What's CFP? Here we have designed and propagated this hot CFB. We can say sketch here. Here is the reactor. It's here. And we have insulated. And finally, we have covered with aluminum sheets. And here there is the cyclone. Reaction takes place in the riser itself. And at the outlet, we have cyclone for capturing the inventory sand or unburned coal or solid fuel, which recirculate again to the reactor. For reading temperature. This one for sampling. We have used tether bag for collecting flue gas. Here's the feeder we used to put coal and biomass. Rotameters for controlling oxygen, carbon dioxide, air, for aeration and primary inlet.
Here we have CO2 cylinder, oxygen cylinder, regulator, heater especially for CO2, the PCE, very unique.
And we have used a static mixer for mixing CO2 and O2.
From air, oxygen, CO2, the outlet, primary.
And here, entirely it has been fabricated, this setup in the workshop here. And here, this is the experiment for both of coal and for biomass. We can say for oxy-biomass combustion, and here for coal combustion. We can say the variation of stoichiometric ratio 3, 2, and 1.25. Temperature, it goes up to 1,200 for coal, and this could be minimized using enhanced solid recirculation rate, side by side with using external heat exchanger, because we have problems of agglomeration and ash melting for high temperature. That's why it's recommended to use range between 800 up to 900 degrees centigrade. Here for biomass pure oxy-pure combustion, we can see for 1.25 stoichiometric ratio, we have this temperature profile here directly at the level of fuel entrance, and we can infer from this point instantly those sawdust firing whenever it does enter to the reactor. Meanwhile, for the coal case, we can see here is the entrance for coal, but still the combustion, the temperature of the combustion, it's maximum at the bottom of the riser itself. That does mean those coal particles with higher density lying at the bottom of the CFP and firing at the early beginning at the bottom, and whenever it's shrinking, fly along the riser. Comparing with this biomass, here it's smoother, and we can say here represent an instant firing or reaction of the sawdust. For three cases, 1.25 stoichiometric ratio, 2 and 3. For 1.25, it gives the highest temperature and almost its uniform shape. For this case of coal and biomass, we have compared between this work and which we have done with green, it's plotted with green color, comparing temperature profile with results of this from Paul and Silscale, Kert et al. In 2010. The main temperature for both of them almost the same, and for this case we have for green one oxy-fuel combustion, pure oxy-fuel combustion with lambda equal to 3. Meanwhile, the second one, they have used mixture of CO2 and O2, oxygen and carbon dioxide, with percentage of 35 for oxygen. Here for the biomass, we have even used three cases, 1.25, 2, and 3. That does mean this hypothesis is proved using the experimental work. Summary of hot unit study: the key finding, the pure oxy-fuel combustion for CFP combustion is achieved experimentally using coal and biomass as a fuel. This small step toward third generation for using pure oxygen. There is no recirculation of flue gases. What does it mean there is no recirculation? There is no need for setup to recirculate the gas. There is no need for fabrication and the cost of fabrication. There is no need for operating cost also. CO2 concentration is promising and exceeded 70% for lambda equal to 1.25. The particle size of fuel shall be optimized to avoid concentration of the fine in the lower portion of the riser. And here we conclude the work with thermodynamic analysis for the fuel itself, side by side with the firing. Fuel and reaction energy analysis. Here we have this plot. It's representing the percentage of oxygen to carbon with hydrogen to carbon, and we can see here we have four types of fuel: biomass, peat, lignite, bituminous, and we have plotted according to the percentage of oxygen and hydrogen. Here the variation of carbon with fuel ratio, oxygen by carbon and hydrogen by carbon also. Here we have used a sample and sawdust, those for reference. chemical reaction exergy and energy analysis. For each system, we have the inlet, outlet, and in the common stats we have calculated exergy and energy. And here we can say exergy and energy chemical reaction of air fuel combustion, the effects of exhaust temperature over energy and exergy. Here, whenever the exhaust temperature increasing, the exergy dropping because we are losing more exergy. And here the loss of exergy increasing with increasing of the exhaust temperature. Yeah, the same general trend for energy also is dropping with increased temperature for exhaust, but we may see there is slight drop for energy comparing with energy. The same thing for preheating. Whenever we preheat the inlet or the oxidant, we can see there is enhancing in the exergy along with increasing the temperature of oxidant. Here we have compared between the exhaust flues with different stoichiometric ratio and ambient temperature. Whenever the ambient temperature increasing, the loss of exergy is increasing, and for stoichiometric ratio, whenever it's higher, in all cases the losses are much more. The same trend for energy. Here for the energy chemical reaction, exergy and energy of oxy-fuel combustion, we have compared between the exergy for different cases, here for air and for different oxidants with different concentrations of oxygen, from 21 up to 90% of oxygen. We can say exergy is improving this variation of oxygen for reactant temperature, improving with higher concentration. Here the effect of preheating and flow gas temperature. Here for preheating, here for flow gas temperature. We can say whenever we are preheating, the energy increases along with preheating the oxidant. And here for flow gas, whenever the flow gas temperature increases, that does mean they lose much more. That's why we try to observe or extract as much as possible from the flow gas till the point of the dew point for SOx and NOx, to avoid formation of acid of sulfur and nitrogen. Here we may conclude this energy and exergy and energy study is considered as a fundamental one. It gives an elementary results of the effects of reactants, temperature, products, temperature, oxygen concentration in the oxidant, and stoichiometric ratio over the exergy and energy for combustion. Applying pure oxy-fuel combustion could lead to the lowest loss of both energy and exergy. Moreover, at this level of pure oxy-fuel combustion, it's promising to minimize the cost of oxy-fuel combustion. We may conclude with the increasing for this, the cold study. Increasing flow rate leads to higher bed voidage and lower suspension density. And the increased operating pressure decreases the bed voidage due to the higher gas density and vice versa, and the suspension density increases. The increased aeration velocity increases the solid recirculation rate slightly, almost 2 kg per square meter second. And the study of rate particle size effects shows that higher particle size leads to lower bed voidage due to increasing the particle terminal velocity. And finally, this interestingly, the terminal velocity for air and mixture of oxygen and CO2, it's almost the same. Here for the hot one, the main task of hot CFP unit experiments is verifying the possibility of using pure oxy-fuel combustion. Whatever we have, it's the core of this work. We have proposed pure oxy-fuel combustion, and experimentally we have proved. And here the average temperature along the riser for biomass and for oxy biomass using biomass, so dust as a fuel, and oxy combustion case. We have got 1,129, 1,051, and 961 for dust stoichiometric ratio. So the temperature itself is a function of the stoichiometric ratio. The same thing for cold, bituminous. For bituminous use as a fuel. The temperature profile along the riser is more uniform for oxy biomass CFP combustion comparing with oxy-cold CFP combustion, because the density of biomass of the sawdust less comparing with coal, and the fine particle, it flows smoothly comparing with coal. Using pure oxy-fuel combustion, 100% we have already used and proved the flow gas is reduced 5 times. That does mean we have no enough gas to absorb heat and waste it to atmosphere. Biomass, namely sawdust, is used as a fuel and gives a better uniform temperature profile along the riser compared with coal firing case. Applying here for the analytical exergy and energy analysis, applying pure oxy-fuel combustion technique minimize the loss of energy side by side with exergy. And exergy fuel analysis gives better accurate values of fuel with ash concentration in terms of lower heat value and higher heat value. Different fuel types could be used for the same load. We may use the exergy analysis for fuel whenever we are going to replace coal with maybe biomass. We may calculate the equivalent value of this biomass based on the exergy fuel. The increased exergy of oxy-fuel combustion case due to the preheating increase with decreased percentage of oxygen in the oxidant, mixture of CO2 and O2. Excitingly, the gained exergy of air combustion case is similar to that one for mixture of CO2, O2, 10%, 90%. Finally, the gained efficiency of pure oxy-fuel combustion recovers the penalty of air separation unit. is the scopes and future work. Actually, there is nothing perfect, and we cannot achieve anything 100%. So here there are some scopes and future work students may continue with. For instance, we have used mini CFV. The CFV could be scaled up, and heat exchanger, external heat exchanger could be used, because for the oxy-fuel combustion, the rate of heat release is much more higher. So we need augmented solid recirculation rate. That's why we may use external heat exchanger. The effects of oxy-fuel CFV conditions are studied using mini CFV. We may in future scale up. The effect of operating pressure is studied between 100 kilopascal up to 250. This one we may go beyond 250, because for liquefying CO2, if we use higher pressure, we may get direct liquefied CO2. That minimizes the cost of processing of the flue gas. It's suggested to find the effect of replacing air with mixture of CO2O2 for big CFV scales running. As we have seen, there is no significant difference between using oxygen, mixture of oxygen CO2 and air. But maybe for bigger scales, there could be a difference. Finally, the temperature control based on stoichiometric ratio could be used for maybe pulverized coal power plants or solid waste firing. In this present study, the investigation are done by conduction short-term test, and it could be run for longer test for maybe finding the problems of SOx and NOx and corrosion. A comprehensive techno-economical analysis of pure oxy-fuel combustion could be done in future, maybe using Aspen Plus or any software for finding what's the accurate percentage of cutting the cost of oxy-fuel combustion. A comprehensive economic analysis, we have already mentioned. Finally, there is one journal paper and another one we have conducted, one book chapter, 3 conferences, and final fellowship in École Polytechnique to Montreal in Canada, hopefully 2017. Here's acknowledgement. I would like to start with supervisors and ICCR.
Guys, so we have done sufficient work and I will leave this for discussion.
The good presentation, but I have some 5 queries.
Yeah.
I would like you to go back to slide 11.
Yeah. Very good.
For a recirculating fluidized bed,
Yeah.
and for a normal single no recirculation
Yeah.
fluidized bed,
Yeah.
how the graphs will differ? Will they differ, or is there any difference in the bed voidage and the suspension density?
Yeah, there must be a difference between both of them. I think we have for fluidization, for fluidized bed, we start with bubbling bed. For bubbling bed, there is no entraining of the particles outside of the reactor itself. It's just like boiling. It's two-phase flow. And here, what we mean by bed voidage. Bed voidage is for two-phase flow. Suppose we have 25% solid. So the 70% represent the voidage. So in this case, whenever we have solid at the bottom, that does mean the solid is maximum and the voidage minimum. So the graph itself, it could be sharp comparing with this one. Because here we have voidage, so the voidage itself could be, or here is the height, here is the voidage. At low portion, the voidage will be minimal. Whenever we go up, the voidage will increase because there are minimum amount of particles. For CFV, we are using recirculation. It could be smoother. And we have another third type of pneumatic reactors. For pneumatic reactors, almost the particles velocity does have the same velocity of the gas itself. So it becomes much more smoother. Here's the voltage, here's the height.
I feel since the process is same in the column,
Yeah.
air flow and the particles dispersing. So there should be same graph, why really there should be difference like what you are showing. What is the recirculation?
We have two things to clarify.
Yeah.
One of them, why recirculation, and another thing, what's the effect of recirculation. First of all, recirculation we use for enhancing the combustion because whenever we have this inert material, it enters to the reactor itself, absorb heat, and goes outside of the reactor for
That is the heat transfer.
heat transfer.
But as such for the water,
For the bed voidage, why it's like that? As I have mentioned, it's two-phase flow. We have gas side by side with solid. So according to the distribution of the particle, we have different percentages of solid particles and different percentage of the gas itself, and accordingly the profile change. And we have one more thing. Whenever we are increasing the velocity, there is something we call steep velocity between the particle. Suppose there is bubbling bed. For lower velocity, it could be almost the same. Here for CFV, the steep velocity between particles and velocity much more higher. That does mean if we have velocity for the gas, maybe 4 meters per second, the particle velocity could be 2 or less meters per second. Whenever we go for the pneumatic one, the steep velocity is minimal. That does mean that particle and gas flows almost in the same velocity.
So now you go to slide 17.
Yeah.
So here I heard you saying as the temperature increases, the viscosity increases. Is it true?
Dynamic viscosity. Whenever temperature increase, dynamic viscosity increase also.
How that's the contrary it should be. As the temperature increases, viscosity should reduce.
It's fluid. There is difference between liquid and gas. For liquid, I think whenever we increase the temperature, it goes down. Meanwhile, for gas, it's a matter of kinetic. Whenever we increase the temperature, it will move and collapse with each other. That does mean the dynamic viscosity is a function of temperature increase by increasing of the temperature.
Please go to the slide 21.
Twenty-one.
21. Right.
20.
Here you are using the last lambda equal to 3 reactor 1.
First reactor. Yeah.
And oxygen, pure oxygen.
It's pure oxygen.
That is what lambda you are using.
Yeah, pure oxygen with this is 100% of O2 and lambda equal to 3. But that means we are using for 3 1% for combustion, for reaction, and 2 third, which is 2 equivalent volume of this one. Just like inert material, inert gas, doesn't take a place in the combustion ideally, just absorb, just like nitrogen.
Like 30.
Yeah.
In that graph, the temperature versus dimension over the sky, we are using coal versus biomass. Lambda 3 for both.
No, there is one mistake here. This one in green, it's the result we have got with lambda equal 3. The second one is for another researcher, Sysgrit, it's from Poland, and they have used CO2, O2 with percentage of 35% of oxygen. So there is
No, both are lambda 3.
no. This one is supposed to be CO2, O2, and the oxygen concentration 35%.
Why the humps are different? The big difference, no? At 0.8.
Actually, for
No, at 0.8 dimensional SI.
200 degrees.
0.8, yeah.
There is big difference. Why?
Here, first of all, coal and biomass. For coal, it starts combustion directly, instantly whenever it enters to the reactor. It's smoother, and here we can say at the higher portion there is less material of insulation, kind of representing heat exchanger. Meanwhile, for coal, it starts combustion at the bottom of the riser.
Last question. When you want to scale up, as you suggested, it should be tried on a
Yeah.
bigger scale.